Now let's take a look at a more technical aspect of the SMPG. So the SMPG is composed of this introduction or the page, which is the raw data sheet, and here we paste all the data that we bring from the geoclim. So these are, here we have the list of as many polygons as we want, and this is the time series for each polygon in decadal time steps. So starting from decade 1 of 1981 and going all the way to current. So in this case, I'm just using a single polygon, and so this is the introduction. Then once uh, in the back here, oops, um, so what runs in the back is this sheet. This sheet has all the formulas, it has all the functions to run the process for many polygons. So what the program does is it copies this sheet into as many polygons we have in here. So this sheet is always hidden. So once we have as many as I've run it for 100 polygons or so, and so it takes the first polygon, it copies that data sheet that is hidden, and it creates this new sheet called with the name of the polygon. Then it goes into the second one, and it creates as many polygons as we have here. So that's why that hidden sheet is so important. So here I'm preparing a new hidden sheet because this is the one that hidden sheet has to be updated with the new settings for the new season or any changes that we've made. In this case, I added the 2020 year because it was only set up to 2019. This is one of the difficult parts of the tool, is that is not automatic in adding the new year. We have to add it by hand, and that takes a little bit of time because we have to add it in different places and all these different tables that we're gonna go over what they do. So we have to make sure that all the formulas are clean, reading, taking into account the new year. So then the tool has that hidden sheet that is the one that contains all the functions. Then it has a couple of tables. It has a couple of extra sheets. One is called the summary table, and we'll see what this is filled with. And then another is the analog years table. So let's go over what is in the SMPG. Let's see, behind the scenes, if we look at the developers part, there are two main modules. One is this function right here. This one is the one that reads the data from the raw data, identifies the years, and then takes all the decades and puts them into in the format in columns, as we see here. So this is the uh, each year is put into a column. Then the other one is this function that has this is the one that copies the data um, sheet and gives the name based on the name of the polygon and creates a new sheet with that name. So make sure that you know what you're doing if you're gonna make any changes to this. That is the code behind the whole thing. The rest of the formulas are in the data sheet. So let's go over each of these components. So the first thing that we have is this table over here. This is the first thing that is created once we run the tool. So what this is just here in column A is the decades from decade 1 in January. This is just a white placeholder there as a background. So here we have the 36 decades from first decade of January to the third decade of December. Then here we have the numbers of decades of each decade. And here we have from decade first to 36. That's all it does right there. And then we have each year in by decades. Then here at the end we have a column with the long-term average that is calculated from 1981 to 2010, and based on this graph then we create this plot. This plot is showing the long-term average, this red line, and the current year. So this is just test data that I added just to since I just finished that in the 2020. Okay, so that's the first table. Then the second thing that we need to set up our tool is to put here what is the starting decade for the season that we are going to analyze and the ending decade. So here I'm preparing to run the bell season in Ethiopia, so I'm going to run it from the first decade of February to the third decade of May. So we do it here in the blue, in these two blue cells. We don't touch this right here because these are automatic change to when we made a change right here. So here we select in this case I'm going to select the first decade of February to the third decade of May, and that determines many things. In the plots, that sets up the x-axis on both plots. We're gonna go over the plots, but then once we made that change, we'd set up the plots, and once we make that change, we are impacting this section right here. This section, clean this up that I was doing some tests. So this table is the brain of the whole thing. The first thing that we do with this table is set up this column right here. This is a column that is 36 decades long, and this is a new series, a new sequence of 36 decades, starting by the first decade that we just defined in the season. So this is telling us this is decade one of the new new year, or the new 36 decades, starting from decade 4. That was the decade that we defined in the start of season, and in here, right? So that's decade 4. So the starting decade is decade 4. So the decade 1 of the new sequence is decade 4. Then from here on, we continue with 36 decades independently, that we go over the next year, the following year. This one right here, this is the place in the new sequence here in this new 36 decade sequence. This is the place where the end of the decade for the season that we are analyzing falls. So if we go back here and we are saying that our last decade is decade 15, then we come here and decade 15 is right here, and the value in the new sequence is 12. So that is the place on the new sequence. This one right here is the place where decade 36 of the old sequence would fall in the new sequence. So if we come here, this is 36, is number 33. This is to define what is current year and what will be the following year. So those these parameters are very important to keep clean, not to change, because they change automatically. So this column right here on A for the starting the index is defining if the current date is part of the date is part of the current year, and that's how it it gets the data for each of the decades based or either in the current year or the following year. So that's how this table works. So once this table is done, that's table 2, then there are a series of more tables that is this table in blue that is based on this table in white right here, and this is the calculations, and this is the plotting. The blue table is for plotting the calculations of the seasonal accumulation. Then we come down here, and this yellow area or this table is based on this other white table down here, and this is for the ensemble. So this is the calculations for the ensemble, this is the plotting for the ensemble. So, and below this is this is for the analog years. So that is the whole picture. So now let's go back and review each of those um, tables. But before we do that, so this is the analog years, and we come here to the analog years summary. So this section right here summarizes that section below with the analog years. So these plots, as I mentioned, those are produced using those tables below, and all the values in the summary statistics are based on the tables below or are linked to the analog years. So what this means is this calculation here shows the average taking into account the analog years only that we have selected, and this one gives the value taking into account all the years. What that means is that here we come and we decide if we want to show or not one of the years. For example, if we want to um, deselect years, we change the 1 to 0 for as many years as we want. So I'm just taking the ones that are high values, higher than 10. So as I'm changing there, this is taking out of the plots all those years that I am changing into zeros. That also has an implication in this one. So these values are now based only on the analog years that I have selected, and it takes out of the process those years that I just changed to 0. But this one keeps giving us the values for all the years. And what it did is it takes out from these plotting tables, it takes out those years that we just changed to 0. So it took them out of this one, but this one, that is the calculation for the seasonal accumulation, is still complete, and also this one is the ensemble table for the plotting. So this one reflects what years we took out of the uh, analog summary. So this is the calculation for the ensemble. Let's take a look a little bit about the summary statistics. This summarizes the climatology, so it tells us the average, the median, the standard deviation, the terciles, and this one right here is giving us how much of the average up to the current decade, what percent of the average we have accomplished. So this is telling us percent of average at the current decade. This summarizes now then using the ensemble. So the ensemble takes into account the observed to the current decade, and then it completes the season with the historical data for each of the years. So that new data set is here then summarized. This is the average of that new data set, the standard deviation, and so forth. And this one is the outlook. So this is looking based on the ensemble, and so it looks into the number of years greater than the 67th percentile. This is taking into account only the analog years, and then this is the taking into account all the years. And based on those, then we come up with the probability of being at the end of the season being above normal and below normal. Here is an example of running many polygons. So these are all the polygons in Ethiopia, and I just run the entire country. So the data sheet that is hidden was used as a template for each of the of these polygons. So here we have, and this is the way I like to get it, because once I open it, I can just select the three plots and copy and paste them into the report. These polygons are starting way behind, below the average. So we were talking about the analog years. So let's go down and finish talking about the analog years and explain how we calculate analog years. There are two criteria. The first one is comparing the sum of the current season up to the current decade to the sum of a year. So here we have, this is the sum up to the current decade, and we get this value from here. So this is the sum that we have up to the current decade, and then we have the corresponding sum for 1981 and 1982 and so forth. This value right here is the difference squared. So it's the sum of the current year minus the sum of the corresponding year squared. So this is the square difference of the sums. That's the first criteria. The second criteria is comparing decade to decade. So this is the square difference of the comparison of the decade of the first decade of the current year, or as we define as the season. So this is the first decade of the season compared to the corresponding decade of 1981, the difference square, and this is the same process. Then we sum that difference square. So this is the sum of differences squared decade by decade. We rank those values. That's the first rank that we do. Then we rank the sum error, the square error of the sum is ranked right here, and then we sum those two ranks, and then we rank that sum. That is the final product. This one right here is the corresponding values, or the values that we are showing right here in the summary of the analog years. So each of these values corresponds to the values that we just got below. We compare the sums, and then we compare the decade by decade. To summarize the analog years results for all the polygons, so then we have here the analog table. This table then gives us the information for each polygon, which one is the analog year that is closer, and the second closest, the third, and so forth. And it changes for every decade, because as we saw, is based on the observed data. So this is then how the SMPG represents each of those polygons, and then provides the summary tables so that we could then create the maps.